All right, today we are doing two proof-oriented triangle theorems. This is going to kind of build on a little bit of what you did yesterday. Our objective is to apply the no-choice theorem and the angle-angle side theorem. Now, this one here isn't necessarily a way to prove triangles are congruent. This one is. Okay, this goes along with angle, side angle, side angle, side, 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 and hypotenuse leg when you have right triangles. So this is going to be a fifth way of proving triangle congruence. Okay, let's start off with the no-choice theorem first, though. This is Theorem 53, and it says if two angles of one triangle are congruent to two angles of a second triangle, then the third angles are congruent. You can shorten this by saying the no-choice theorem. Okay, so let's say we're given that angle A is congruent to angle F, angle B is congruent to angle D. We know that triangles can only add up to 180 degrees. So if A and F are congruent and B and D are congruent, that means together they add up to the same amount, which when you minus that from 180 will only leave the same amount in both. Okay, so our conclusion would be that angle C has to be congruent to angle E. Something to note about this. This is not necessarily a way to prove triangles are congruent. Okay, you do not need congruent triangles, because remember, these are three angles. Obviously these two triangles are slightly different in size, but their angles are the same. So we wouldn't be showing them congruent, we would be showing that the angles are congruent, which could then help us prove that two triangles are congruent. So this isn't necessarily a way. You can't go from this to CP/CTC. Okay, this would be a way to help you prove that triangles are congruent. All right, so Theorem 54 states that if there exists a correspondence between the vertices of two triangles such that two angles and a non-included side, okay, so it's not in between the two angles, it's angle, angle, and then a side, of one are congruent to the corresponding parts of the other, then the triangles are congruent. So like, let's say I had these two triangles here. I'm given that angle E, why isn't this working here? There we go. Angle E is congruent to angle K. Angle F is congruent to angle M. And DF is congruent to OM. I need to prove the triangle DEF is congruent to triangle OKM. Now, first things first, you can state all your givens. Okay. Next, we could say that angle D is congruent to angle O by the no-choice theorem, because we've got two pairs of congruent angles in a triangle. And now we can say that triangle DEF is congruent to triangle OKM because of angle, side, angle, angle, side, angle. So like I said, it can help you prove triangle congruence, but you can't prove triangle congruence with this alone. So that's the main thing that I want you to take out of this. All right, so those are the only two theorems that you have to learn today. So let's go ahead and apply that here and see how that would help us with this. So we are given angle RKM, and let me change the color here so that it doesn't get too confusing. Blue looks good. Angle RKM is congruent to angle OMK, and we know that MR is perpendicular to KP, and that KO is perpendicular to PM. So what that does, that tells us that these are 90-degree angles. So we would start off angle RKM is congruent to OMK, MR is perpendicular to KP, KO is perpendicular to PM. And that's our given. Okay, so what would you do next? Well, I've got triangles that I need to prove by RKM, so I need to prove these smaller triangles are congruent. There's a few different ways you could do this. You could say that angle RMK is congruent to angle OKM, angle RMK congruent to angle OKM. No choice theorem. Because we have two angles of each of these already. And then you could say that KM is congruent to KM by reflexive. And then you could say that triangle RKM is congruent to triangle OMK, and that would be by angle side angle. Okay, the other thing you could have done is just skipped this part here. Okay, you could have skipped this, said that, and now you would have had two angles congruent in each one, and then a non-included side. So that would have been angle side. So that's a way that you could use both theorems to prove this. Angle side shortens it by one step, but if you don't happen to see that, you could go with the first way that I showed you. So that's two different ways you could solve it. Yeah, one way is a little bit shorter than the other, but it's entirely up to you. I don't care how you do these proofs as long as they make sense. So anyway,